microphones. Okay, good. So for this session, it's a pleasure to start with Samyak Prasad from Madju Lab in Singapore. So from the CNRS and also the National University of Singapore. So with that, let's, we're still a few seconds ahead of time. Okay, now it's time to start.
Okay, thank you so much for the introduction. Just to introduce a bit more, I'm a postdoc in the group of Alexia Fev, and what I want to present to you today, or talk to you about, is an ongoing research in our group, which has been done in collaboration with Kian Laverick and Maria Maffei. So here we are going to talk about a connection between quantum indistinguishability and purification, right? So what do I mean by purification here? So let's begin. What I mean is quantum state purification, transforming a mixed state, initially mixed state, to purer states. And purer states are states with zero entropy, and I want you to think about pure states as states with zero entropy, because entropy is going to be our metric that we are going to use for purification. All right? So why do we want to do purification, first of all? So as we all know, pure states form resources for quantum technologies. And for example, in any quantum algorithm you would have seen, you ideally begin with pure states. So how do we purify a mixed state? There are multiple purification strategies, one being quantum cooling algorithms, where entropy from the system is funneled out into a bath, reducing the system's energy also in the process, which takes the system to the ground state. There's another way of purifying the quantum system, which is the measurement and feedback done by a Maxwell's daemon, where entropy is rather funneled out into the memory of the Maxwell's daemon. Here I'm going to share with you some preliminary results where we are going to take a different strategy. What we are going to talk about is measurement back action to purify the quantum state. And here I'm going to show you a different way of looking at the same purification process, which will encompass a classical and a quantum mechanism. That's what we're going to do. So let's begin with a particular task. Our task will be purification of a mode, which is a multi-level system, using just a qubit Q. Okay, that's our task. So in this, how do we do this? We do this via this measurement and back action process. So the first step for that is correlating the mode and the qubit. So this is a unitary transformation that correlates them. And in this process, the qubit mode entropy does not change, of course. It's a unitary process. Next, there's a measurement on the qubit. For simplicity, I've taken the measurement in the plus minus basis here. Now, what this does is, if the qubit is measured in the state plus, there's a back action on the mode, which prepares it in the state rho plus. While if the qubit is measured to be state minus, there's a back action preparing the mode in the state rho minus. But here, importantly, what we do is that we don't throw away the qubit states. We keep the measurement statistics or the measurement record, and the final state that you have is given by this rho AQ, where p plus and p minus are just the probabilities of measurement of plus or minus state. Okay. In this case, of course, there's a change of entropy, right? The total change of entropy comes from either the change of entropy of the mode that you're trying to purify, and here it is the average mode entropy conditioned on the qubit outcome, right? So this is what we are going to see. And the other contribution to the total change of entropy is the change of entropy of the qubit itself. Now here I'm going to talk about entropies in bits, because we have maximum 1 bit of information that we can store, hence maximum 1 bit that we can purify. So everything will be in terms of bits. So here, of course, the qubit entropy change is bounded by 0 and 1 bit. Okay. So here we see an entropy increase because of the measurement, which is the change of the total entropy. And this is the measurement entropy because of the irreversibility of this process, of the measurement process, right? Now what we want to do is reduce the average mode entropy of the, reduce the average mode entropy, or make this change as negative as possible. So I can define a metric of performance for my purification. This is given by P here, the purification, which is just the negative of the entropy of the mode conditioned on the qubit state, no change of entropy of the mode, right? Now this purification is interesting. for this measurement and feedback operation that I just showed, it's always greater than 0, and these are results that have been published before. It's always greater than 0 if the measurement of the qubit is efficient. Okay? We can discuss later what this efficiency means, but for now, believe me that it's greater than 0. And of course, it's bounded by 1 bit because we just have 1 bit of information to extract, right? Now, one way to think about the entropy flows in this scenario is that the entropy transferred to the qubit here either comes from the correlating step, which is good, which is used to purify the mode, or goes into the measurement entropy, which is bad. This allows us to define an efficiency of the process given by just the purification divided by the change of entropy. Intermission? Any questions? Hello? Yeah. Hello? Yeah? Okay. Okay. So just a quick recap. We have what we have defined here are figures of merit, where we have the purification given by the negative of the change of the conditional entropy of the mode, right, which is always greater than 0. So we never have an increase of entropy of the mode because of this process. Either the entropy does not change or decreases. And we can also define the efficiency, which is the purification divided by the change of entropy of the qubit itself, which is 1 minus the measurement entropy, which is bad, by the qubit entropy. And this efficiency is bounded between 0 and 1. All right. With this will be the protocol. Now let's look at a different way of analyzing purification or the change of entropy. All right. Now let's imagine a transformation rho 0 to rho. Good. I express rho 0 in a diagonal state. So let's say it's a distribution P0 over the Fock states of the mode. Right? It's a some mixed state. Now it transforms into a state rho, and now I make a choice. I choose to express rho in terms of a distribution P tilde over some pure state psi n, where these psi n's might not be orthogonal. Okay, I make this choice. Why do I do that? Let's actually analyze or look at the change of entropy of rho, how the entropy changes from rho and rho 0 to rho, right? So now I give a splitting that depends on this choice that I've made. Okay, so the change of entropy is given by the entropy of rho, of course, the von Neumann entropy, and by H I denote the Shannon entropy, and this is the Shannon entropy of the this is the entropy of the initial state, which is the Shannon entropy of the P0 distribution. So this is just the change of entropy, but here I add and subtract the Shannon entropy over this P tilde of this P tilde distribution. Now with this, what I see, this part just talks about the change of population. If the entropy of the Shannon entropy over P0 distribution is greater than the Shannon entropy over the P tilde distribution, we get something called classical purification, what I'll classify as classical purification. While the other part is the difference between the von Neumann entropy of rho and the Shannon entropy over this P tilde states. What this captures is the non-orthogonality of these states psi n, or what I call the partial indistinguishabilities of the state psi n. Okay? And because of a theorem related to Holevo's theorem, which actually limits how much classical information can be extracted from quantum ensembles, we see that the Shannon entropy over this P tilde distribution, which is essentially imagining that the P tilde distribution is over orthogonal states, is always greater than the entropy of rho itself. And this is the origin of what we'll call quantum purification. So for now, this is very abstract, let's take some examples. Okay, let's start with classical purification, where we are going to do a parity measurement, right? So let's say my initial state is rho, again, some mixed state over Fock basis. And the initial entropy here is 2. This is the distribution over n. Now what happens because of this measurement and back action step, if the qubit is measured in the plus state, you get a state rho plus, which is just an even parity state. This has 1 bit of information. While if the qubit is measured in the minus state, it is the odd parity state, and this also has a 1 bit of information. So here what do you see? You see just that the P0 distribution has changed to P tilde plus or P tilde minus because of this back action, right? So the cause of purification in this case is just the change of the probability distribution over the same states. So here this is what I'll call classical purification on average, and here the classical purification is just 1 bit, and this is the maximum that you can attain using a qubit. Let's talk about quantum purification now. Now imagine, now we have some distribution over Fock states again. Now I want you to imagine that this measurement back action step, all it does is maps the Fock state n to some state psi n plus or psi n minus conditional on the qubit outcome. Right? That's all it does. That means if the qubit state is measured in plus, you get the same distribution P0 over the psi n plus states, and similarly when the qubit is measured in state minus, you get over the psi n minus states. Right? Here importantly, these are states, but they aren't orthogonal. So this is what I depict here. It's the same distribution, but they are overlapping states. Right? In this case, we have seen already from the theorem related to Holevo is that the entropy of the state rho plus is always lesser than the Shannon entropy of P0 here. But this Shannon entropy of P0 is just the initial state entropy, and this is true in each case. So then we get purification, the quantum purification that is induced by this indistinguishability of the psi n states, right? And this is always greater than 0. This is strictly greater than 0 in this case. Now, can we see this in real experiments? Are there real platforms where we can use quantum indistinguishability to achieve purification, right? So let me talk about a pretty famous example of experimental setup, which is traditionally used to create cat states, right? So let's just talk about the experimental sequence. Let's imagine the mode is prepared in the vacuum state, so 0. This is the phase space distribution, while the qubit is prepared in the plus state. My correlating step here will be conditional displacements with alpha very large, right? So if the qubit is in the excited state, it displaces the state to alpha, while if the qubit is in the ground state, it displaces to minus alpha, right? I make a measurement in the plus minus basis, which does the back action, and this is what creates cat states. So I am sure you would have seen these are very famous states, the Schrodinger cat states, which has the interference fringes here, and these are the conditional states that you achieve. What happens when you initialize the mode in a mixed state? What you get are conditional states which are cat-like mixed states. These states have actually been experimentally implemented in superconducting platforms where they had used thermal states, and they were called hot Schrodinger cats already in the references here, right? What we are going to do is we are going to use this experimental sequence in order to purify the initial mode of the cavity. This is what we are going to do, interestingly. Let's see what happens. So I have some distribution. Let's say it's a thermal distribution over multiple Fock states. This transformation changes the distribution and changes the overlap of the Fock states, right? So there is the two effects. Here I didn't, because before I told you that the expression of rho plus or rho minus is dependent on you. It's a choice, right? So how do we choose these psi n plus and psi n minus to extract some useful information? So here I choose to express rho plus and rho minus in terms of the psi n plus and psi n minus, which are nothing but the transformation of each Fock state via this conditional displacement protocol, all right, and the measurement. So you get psi n plus, which are given by d alpha, plus d minus alpha, which is a non-unitary transformation of a Fock state. More importantly, these states overlap, and their overlap is proportional to the overlap of the coherent states themselves. Okay? In this case, we get both classical and quantum purification. As you can see, this is the purification that you observe. I can do the same trick of adding and subtracting the Shannon entropy over the P tilde, and what we see is the average classical purification and on average quantum purification, right? So let's see in which range of parameters can we actually attain purification and why. So here I plot against the displacement parameter alpha, the purification. At alpha equal to 0, nothing happens. You don't do anything. So the rho plus and minus states are just rho 0. At large alpha, it's interesting. These are the cat states that I showed you, right? We attain no purification because the rho plus and minus states are nothing but the same probability distribution over orthogonal states. So there is no quantum purification, neither is there any classical purification. For small alpha, what we make conditionally are kitten states, are mixed kitten states, let's say, where you can see that the blobs are indistinguishable, right? Here, we have a change of the probability distribution to p tilde, and we have non-zero overlap here. So this is the reason why we can achieve purification even in an experiment where purification was never thought of. So this is just using a qubit, and we have purified a mode, right? So let's talk about maximal purification via this process. Okay, so we begin with the initial state of the cavity. Here I restrict the dimension of the state or the support of the state to some d, all right? And I plot the optimal purification against alpha, where I optimize over the p0 distribution, okay? So this is the best purification possible via this protocol for each alpha. What you see is that purification is observed in regions where the overlap is large, right? And that is, the alpha is small, essentially. Now, as we increase the dimension, so each line corresponds to the dimension of the cavity that I've chosen, and as we increase the dimension, you get more and more purification. Here I plot the same thing, taking the maxima by optimizing over all the alphas also against you. Okay. Yeah, now I think I'm done. So here we see the optimal purification via this protocol increases with the initial support dimension of the mode, which is interesting. And this is because the quantum purification also increases with this, right? As you go to higher dimensions, you get more and more quantum and classical purification by this process. And moreover, this process is also efficient, entropically speaking. If you remember, I defined the efficiency as the purification by the entropy change of the qubit. And surprisingly, for me at least, this efficiency is pretty large. It's 0.7 when 1 is the maximum. So this is very efficient. These are very efficient in purifying the mode, high dimensional mode here. So this is what I said. And with this, I would like to conclude. So here we have proposed a new mechanism to look at purification protocols, right, based on measurement and back action. And we have identified quantum and classical contributions to them. We have proposed experimental protocols to achieve this, which are traditionally used to study Schrodinger cats, right? And we showed that the protocol performs well in regions that are not well studied of the same protocol. Now, this study can, of course, be extended to ancillary systems that are not qubits. But for me, interestingly, what is interesting is if you imagine the correlating step removing energy, you can move the whole distribution closer to vacuum. So you can achieve quantum cooling via this process also. And that I would be also very happy to discuss with you all. So with that, I would like to thank you for paying attention. Yes.
Okay, so questions. So we have one here, so let's start here and then maybe over there.
Thank you, Prasad, for your talk. I have a quick question. On slide 4, you mentioned that you change entropy autonomously. What does it mean?
I didn't.
You change entropy of the qubit autonomously. So
no, I didn't. It's not autonomous. You measure the qubit,
okay.
right? You make the measurement of the qubit, and the entropy of the qubit changes, of course. Oh, sorry. Yeah. So the entropy of the qubit changes because of this measurement on average over the measurement outcomes, and that feeds into purifying the mode of the cavity, conditional on the state of the qubit.
Oh, there is no autonomy because you mentioned
no. There's a measurement from the outside. Yeah, there's no autonomy. I'm
okay.
sorry if I mentioned autonomy.
Okay, thank you.
So I have a question which can be quite silly. I don't know. It's about my ignorance about quantum thermodynamics. Sean M. Carroll has this 2021 paper about energy conservation in extremely unbalanced quantum systems. So my question is that what are the conditions and limitations of putting von Neumann entropy and Shannon entropy in the same formula? So can we do it in extremely unbalanced systems, quantum systems as well?
So first I would like to ask you, what do you mean by unbalanced systems? So I'm not familiar with this.
So in this paper, you have this quantum state which collapses to a very, very high energy. So it is just to prove that the energy is not going to the measurement apparatus. So he has this experimental protocol as well. So you have these two-level systems where one of the well is very, very deep, let's say.
I see. So in principle, there is no issue really regarding this. You can compute Shannon entropies and von Neumann entropies of states irrespective. Yeah, but I think, are you talking about the problem of infinite dimensionality? Is that the problem? Because there is no problem if the states are unbalanced. I don't see it. Okay, maybe we can discuss later. I've not understood. Yeah.
We have time for one more very quick question which only requires a quick answer. Is there anyone who hasn't asked a question before? No? Okay, so they go ahead.
Very interesting result. Can this be actually formalized in terms of a resource theory?
Yeah, so I'm trying to work towards that, exactly. But here, we are using measurement, really, as of the qubit as a resource in a sense, because everything is happening at the same time. You make the measurement, you have the back action, right? So I'm not sure how to do that. We can discuss.
It's hard to define what is free.
Yeah, what is free, exactly.
Interesting.
Yeah.
Perfect. Short question, short answer, excellent. So let's thank Samyak again.
Thank you.